Hello, welcome to Seasonal ARIMA forecasting. So before I start talking about seasonal ARIMA, let's have a ARIMA review. So that's ARIMA, right? Autoregressive integrated moving average. Now the autoregressive part, it uses past values to predict the current value. The integrated part, or D, is difference to remove trends and make the series stationary. And then the moving average uses past forecast errors, in other words, residuals, to improve predictions. So here's the formula with a combination of phis and thetas, the phis being the autoregressive components, and the thetas being the moving average components. So we've got the AR coefficients, the MA coefficients, and the error at time t. And if differencing D is used when YT means the differenced series, okay? And it's not raw data. We could say, we could shorten it and just say ARIMA PDQ, okay? And then so ARIMA PDQ handles trend and short-term autocorrelations, the keyword being short-term. So why seasonal ARIMA? Sometimes data shows seasonality, repeated cycles. So for example, Amazon, monthly retail sales peak in December every year, right? And then we've got something like Lyft. Lyft rides peaks at 5 p.m. every day after work, right? That's an example. A standard ARIMA won't capture this repeating seasonal effect. That's why we extend it to SARIMA or seasonal ARIMA. So here's the seasonal ARIMA equation. We've got originally the phis and the thetas for the autoregressive equation. Now we add seasonal terms at multiples of S. So we've got that second term, the seasonal ARIMA, the seasonal autoregressive, and then the seasonal moving average, right? So we've got those two components added. And you see the T minus S and the T minus 2S, right? Which are the multiples of each other, right? Same with the moving average component, the seasonal moving average component, T minus S, T minus 2S. So you see that the seasonal AR coefficients, the seasonal MA coefficients, and then the seasonal period, right? So this could be 12 months, like I was mentioning in the Amazon example, or it could be 24 hours, as I was mentioning in the Lyft example. So we have two opportunities to difference the series. One at a shorter lag, right, which is just the irregular non-seasonal ARIMA component, which eliminates short-term trends, making it stationary, and the other seasonal lags, which makes seasonal trends stationary. So there's a number of ways for checking for seasonality. We could do the visual inspection of data itself. Here's an example of Lyft rides. You could see that it's basically cyclical around 24 hours. We could check the plot ACF of the data. And here you see some really clear patterns, almost like sine waves, right? Or they actually are sine waves. And then we could finally seasonally decompose data and then check for some type of signal. So if you see the third graph, we could see that that's the seasonal component Above is the trend component and below is the residual component. But you can see that the seasonal is much more clean. So I've worked with data that's actually pretty clean, like a sinusoidal wave, but you're going to see that in other data sets, it might not be as clean as this, but if you decompose the original series, you're going to be able to see a pattern. So here's a SARIMA simplified and explained. The PDQ are the non-seasonal ARIMA terms, like I mentioned earlier. And then the big PDQ are the seasonal ARIMA terms. And then S is the length of the seasonal cycle, right? So I said S is equal to 12 for Amazon for monthly data, and then 24 hours for daily data for Lyft. So before ARIMA could be expressed simply as a trend term plus noise, now SARIMA accounts for seasonality. Now it's trend plus seasonality plus noise, like we saw in the seasonal decomposition. So let's talk about seasonal differencing. So seasonal AR depends on past values from the same season. Example, last year's December sales. Seasonal differencing removes seasonality by subtracting the value from the same period in the previous season, right? So it would look like something like that. S could be 12 to follow up from our example earlier with Amazon. And you could see this pattern, right? You could see that there's this seasonal trend, okay? But if we just difference the seasonal component, right? We take, like, say, the troughs of this graph and subtract it, we'll get something that looks like a graph on the bottom, right? Recall from talking about stationarity, is that it fluctuates around a particular value, right? It always either goes above or below, but it always returns to some level value. Here it looks like around 10. And that would be our stationary series, right? So, and then finally, we've got the seasonal MAQ, and that uses errors from the same season in past cycles. So you could kind of see the big P, big D, big Q as kind of a back shift, right? A lag of like 12 or 24, something like along those lines, right? It's not trying to look at it from a trend perspective. It's trying to look at it from a seasonal or cycle perspective. Now I'm going to be talking about maximum likelihood estimation, and I'm going to simplify a lot of the math because as you know, as you can see that there's more parameters, so it's going to be more complicated. So we started talking about something called AIC, where K is the parameters, L is the log likelihood. And the log likelihood maximizes over all parameters of theta. So we've got all the parameters that we just mentioned, right? We've got it on the non-seasonal ARIMA and the seasonal ARIMA, and of course the variance. So because seasonal parameters enter as lag polynomials at multiples of m, the likelihood surface is highly non-convex. And multiple local optima, flat ridges, and near unit root behavior when seasonal differences d is greater than 0 makes optimization delicate. So I just want to talk briefly about unit roots. This is something that's a pretty important time series, but basically with a unit root, shocks to the error term do not die out over time, they accumulate. So this causes infinite variance where variance is growing with time. And 2, non-stationarity, no stable mean, no stable variance, and no stable autocorrelation structure. That's why ARIMA models often include differencing to remove this unit root and achieve stationarity, right? So I wanted to make that point. It's a little bit beyond the scope of what I'm discussing, but uh, knowing about it now is useful for later applications and uh, later we'll probably discuss building on these theories. So it's important then. So I'm going to optimize models based on minimizing AIC. We've done this earlier with ordinary ARIMA models. We've got the ARIMA PDQ, the large PDQ, and then we could create different combinations of different parameters. So these are our starting parameters, right? We assume that P and Q could be 0, 1, and then PQ is 0, 1, 2. For now, for this example, I'm going to fix the differencing, both the non-seasonal and the seasonal part, and I'm just going to say it's 1, okay, for simplicity's sake. So we could multiply 2 times 2, there's 4 parameter combinations, and then 3 times 3 is equal to 9 parameter combinations. And that leads to a total of 36 parameter combinations, right? That's quite a lot. It's a lot more than what we saw earlier with the ARIMA, where we had 9. Here are the parameter combinations that we have to basically loop through and find the minimum AIC. So here's some pseudocode. Basically results, you have to initialize a loop, right? And then we use this for loop on a SARIMA. We fit it, and then we append the results, right, of the optimal combinations, right, based on their AIC, right? And then we see the results for that, and we get this as our minimum, okay? This is something that we saw earlier. AIC doesn't change for SARIMA, right? It's quite the similar ideas as ARIMA, except like I was mentioning earlier, MLE is a little bit more complex. But with software, it doesn't really matter. So if we reduce this equation, we could say it's a SARIMA with 0, 1, 2, 0, 1, 1, 24. 24 being 24 hours. So here's a lift example with some Python code. It's going to be a little bit of, it's going to be interesting to look at. Well, so here's the packages that you would need, namely this statsmodels.tsa state space dot sarimax import sarimax. Okay, so that's the function. There's no SARIMA function, so this is the one that you should be using. Now it's basically similar. For those that have used scikit-learn, you know that fit, model, fit, predict paradigm. It's similar to this, right? So we fit the order of the model with the minimum AIC, which I showed you earlier, the whole process of that. But instead of the predict, we use get forecast, and then we use steps is equal to 48 to get 48 hours ahead. And then we get the confidence intervals by doing forecast.conf int. And then we could plot it. If you look at the plot fill between, basically we're building our confidence interval here around the actual forecast, which is above, right? So the mean forecast is going to be in red, and the confidence interval is going to be out in pink. Alpha is kind of, showing I guess the color contrast, if it's light or dark. Alpha is equal to 0.3 is pretty light, so it becomes pink. And here's the confidence intervals, like what we're building around the actual data, right? So it's 0 is lower y, and 1, you see the iLoc 0, iLoc 1, those are the confidence intervals, right? So it's going to be 229.86 and 249.57, okay? And that's derived from that conf int variable, right? Where I got the forecast dot conf int, okay? So finally, here's the result. We see the basically the data and then the out of sample forecast 48 steps ahead. Um, the the pink is the confidence intervals. Okay, so that was a little bit of implementation. Highly simplified, I know, but I think it's useful to get kind of the main ideas versus actually using an implementation. But in a future video, I hope to uh, show you something that will bypass this whole um, AIC, process, right? It's going to be all done under the hood. Hopefully you've got the concepts down, but everything is basically abstracted away, and we could just run a simple function, a line of code that will help us make predictions on different types of data sets. Thank you very much, and hope you enjoy this video, and see you soon.